Okay, so we're continuing our discussion on root finding methods. And last time I introduced a new method called fixed point iteration. And we just kind of stopped short of actually implementing it. So let's continue that discussion. So just a brief review of fixed point iteration. So our main problem in root finding is mathematically formulated as finding x such that f of x is equal to 0. We know that we have a lot of functions f where I can actually find this analytically. I don't know, quadratic equation is one of those. We know how to find two roots of that equation. However, in many instances, it's not a nice function f, or maybe I actually have just data, so it's not even formulated as some sort of a function. So how do I go about finding this x? So one way was basically the bisection method that we had before. And the main key of even starting that method is to have a so-called bracket. It's a bracketed method. So you have a bracket where you know the function is negative on one end of that bracket and positive on the other. Therefore, you know it kind of has to, if it's a continuous function, it has to cross a 0 somewhere in between. And then you keep halving the interval until you get close enough to the root. So that's great, but sometimes we're lazy and we don't want to actually look for that bracket. So let's give it another shot with a slightly different method, where possibly I can just start from one guess and just keep rolling. So one idea, and this is how a lot of numerical methods are actually formulated. You look at the problem, you think, well, this might be a good algorithm, then you test it, then you go actually analyze it to see whether it works and whether it can be generalized. So that's a common procedure is, trial and error first and then analyze later. So that's, I guess, how humans work a lot of times. So basically, if I had my x squared plus x minus 1 is equal to 0, then I can rearrange that algebraically into a form that x equals to something else. And there's no just one way to do it. There's multiple ways to doing that. But if you rearrange it that way, then that suggests an algorithm where, hey, you guess first value, x0, let's say, or x1, and then you find that g of x1, and that's your next guess. And then you just kind of keep iterating, and you stop when two neighboring iterations of those are close enough, or there's a difference between it's small enough, and you decide what's small enough, just like in any other iteration. Okay? So if that converges, that's great, right? We will see actually that it doesn't always converge, and I briefly explained what are the situations when it does and when it doesn't. In summary, really, it's going to converge only if the absolute value of g prime, so slope of g, is mild, it's less than 1, okay? So we kind of have to be around, so this will work around the roots where that is true, okay? And that's basically the main limitation. So let's just actually give it a try. So last time, we came up with 3 different options to formulate a fixed point iteration based on the problem B. So if I have x to the 4 minus x minus 10, one version is just to say x equals to x4 minus 10. The problem with that g prime of x is 4x cubed, so I have a hunch that it might not work because that's easily larger than 1. Around 1, it's certainly larger than 1. So that might kind of diverge, but we can still give it a try. There's another one where basically I could take x to the 4 equals to x plus 10, so then take a 4th root of x plus 10, and then it seems that I should be able to make this small, at least in certain areas. And then the third suggestion was here. I did not calculate g prime for that, but there's another option is that x is equal to x plus 10 divided by x to the cube. That should work as well. So let's program 1 or 2 of these and see what happens. I started a little at the end of the last class. So first of all, you kind of define yourself G. Hello? Connection. connection. Okay. So this, hi. Really? Okay. Stay. Okay. Technical. So this is gonna blink now for the rest of the. Excuse me. Let me just disconnect everything and then reconnect and straighten out. Okay. Okay, hopefully this fixes it. So basically I'm gonna say this is a fixed point iteration. Okay. So I'm gonna start from 0. It's just starting from some value. And I'm gonna define my g of x. I'm gonna start with that x to the 4 minus 10 that I have a hunch it might diverge, but we will see. I'm gonna set my epsilon, I'm just gonna call it epsilon now, as 10 to the minus 4. My error is 10 times epsilon simply to be able to enter my iteration. And I'm gonna set iteration count as 0. So this is sort of like initialization of the problem. And actually I'm gonna put everything here. So this is define function g such that x is g of x is equivalent to f of x is 0. So basically you manipulate it and then we kind of initialize. This is my starting guess. This is how close do you want to go when to stop iteration. This basically initializes error to a dummy variable that will allow us to start the loop. And this is iteration count. Allows loop to start. So while my error is larger than this epsilon, I increment the number of iterations. I simply compute my next value of x as the g of starting point 1, right? And that's it for this method, really. This is the core calculation is this one line, right? As long as I have my g programmed, and then I'm gonna recalculate error, so it's basically absolute value between these 2 points. So first I set it to the absolute error, and then I check whether the value I'm about to divide with is larger than 0, and if it is, then I'm going to divide my error. So this is calculating relative error. And this basically says keep iteration moving. So set your x0 to the new value. Is everybody comfortable with my while loop? So this while loop is same pretty much for any method where I'm iterating doing something. The key doing something line is here, The rest is just mechanics of the iteration. Increase the iteration number. Calculate relative error between the computed step and the old one. So computed one is x, the newly computed. x0 is the old one. And then update, right? Update x0 to keep the iteration moving. So this is going to potentially converge, and there's one key piece missing, but I'm going to leave it be and make that mistake. Any hunches of what could be problematic here if the iteration doesn't converge? I'm going to keep going. Okay, so I have no guards right now. So let's see what happens. I'm going to execute this. Nothing's printed. I have a star here saying that I'm computing something still. And I don't even know what's happening, it's just computing. So I actually need to stop that, and hopefully it's going to stop. Yeah, it did. So, and there's a keyboard interrupt. So if I now print this x while in the loop, so basically print every value of x as you're computing it, we can actually see what's going on. Save. Do you see the difference between the previous print and this print? Indent versus not. So when it's indented, it's part of the while loop. So it's going to execute every time that block executes. It doesn't even want to do that. Look at that. It's just stuck. Should have printed something. But it has trouble spitting out the result back to our web page. So what we, there we go. It printed at the end when I stopped it. This is what it means to diverge. Gets larger and larger and larger and spirals out of the control. Error is always larger than epsilon, so it never stops. Okay. So this is very good programming practice, and we didn't do this for bisection, though we should have. Okay. But though in bisection it's less likely to happen. But basically what is a very good programming exercise is set some sort of maximum iteration. And I'm just going to say 1,000. Okay? 1,000, you have enough computing cycles to do that. So I'm going to say and iteration less than maximum iteration. So it's sort of a safeguard that in things diverge, it's just going to stop. So I'm going to say this is safeguard. Guard. I don't know how to spell guard on Friday. For diverging iteration to stop. So if I'm not achieving this epsilon that I want to achieve, it's going to stop. Let's try now. And I'm going to print x at the end. None in between. And I'm also going to print a number of iteration. Okay. Number of iterations and print root estimate. Okay. So everybody comfortable with this guard that I put in? It's always, when you're iterating, always a good idea to put some sort of maximum number of iterations. When things are going wrong and they're not telling you what's wrong, it's bad. All right. Still not stopping. Let's see.
1,000 so difficult to get to? Or is my computer working on something else? What is mine? It has trouble even reaching 13? Wow. Maybe my computer is super slow. Let me safeguard it at 10. So root estimate is this. And it appears to have issues storing this number. So even 10 iterations is difficult. It keeps going. Look at that. So one way to say infinity in computer language. Wow. Okay. So this one ain't gonna work. Okay? Let's try the next one. So this one, I'm just gonna comment it and say diverges. Any questions before I proceed?
So it diverges when the derivative, first derivative is less than 1?
It's larger than 1.
It's larger.
So it just kind of keeps growing and gets out of control. Now let's try this one. So this one is x plus 10. So return oh, look at that. I was quick. When I don't have to handle huge numbers, in 4 iterations, I get close to where I need to be.
Is it known that it says invalid instance now? It was before.
Yeah. It's very nice. It's like somewhere else.
Did everybody get this one?
No, you scroll up, please.
So all I did is I changed the function to be this.
Is there a reason like the 10.0?
Just to enforce the real number. In that huge printout of x, these numbers, they started as integers because it kind of recognized what you start with and then it goes with that, and then they kept being integers, so that whole printout looked like an integer to me, which possibly, this is me guessing, didn't assign it as an infinity because it can handle infinity. It should have just handled it as an infinity once it grew large. And for some reason it didn't, so I thought that it's just smarter to deal with real numbers. Though the moment I put something to the 0.25, it doesn't really matter. So there's a little bit of smart choices that Python does, like it gets the numbers from you, and if it gets integers, it's going to assign them as integers and work with them as integers. And if you immediately put 10.0, you're going to force it to work with a real number, even though 10 in itself is integer. Does that make sense? So I was just trying to be nothing crucial. It annoyed me that it kind of printed that huge integer over 700 pages without recognizing, look, this is an overflow. Recognize it as infinity and move on. Okay? So this was quick. Now, my x to the 4, did everybody get it?
I got
Still not.
5 iterations.
It's still trying to calculate.
Okay, Lingyu, can you come?
I got 5 iterations instead of 4, but it's the same number.
That's fine.
It's the same
exact number of iterations. Is it 5 or 4? Is it 500 or 499? Irrelevant. Part of it is also how are you counting them? Are you starting it from 1 or from 0? It's almost like a philosophical thing. Do you count this initial setup as one iteration or no? Right? So don't be bothered. Like if things actually generally converge, whether you have plus minus 1 iteration, this is not an issue. And sometimes it can be actually a very small numerical error that in your computer or hardware, it rounds things up ever so slightly differently, and then it can be sensitive to this cutoff of epsilon. So that can, but that's a minor. Again, those are minor things if things are actually converging. And now, this thing, we never plotted this function. We just went in blindly, okay? One thing that we could play with here is say, hey, what if I start with something, I don't know, minus 100 and search from there? Will I be as successful? I don't know. This is a complex root. So different starting point. This is 4th order polynomial. It has 4 roots. I don't know how many of them are real because I didn't plot it, so I don't know. Right? So different starting point can get you to a different result or root. Let's try another one, 100, now that I'm at it. This one got to the same one. Okay? So this is part of the problem of the root finding. You're going to find a root, but which one of them? Depends on where your starting point is, hopefully the closest one. But it literally depends on those initial couple of iterations, like in which direction are you set to go.
So will epsilon, we always put 0 first, the 0.001. Will that not change?
Or no, that might change depending on the problem. So you might want to do it with a certain number of digits, right? So this will give you up to 3 significant, like, so when all of your results, yeah, so that would actually require, so if I tell you absolute, so if I tell you the digits to, between 2 neighboring iterations to be the same 3 digits, then you would go with the absolute error 0.001. In this case, it's relative. Okay? It's relative to the size of the root. But that can change based on the root you're looking for. Right? So relative errors you will use when you want generally similar results between different applications, right? Because you're kind of normalizing, so technically same normalized behavior. But if I'm looking for significant digits, then you actually program an absolute error. And all of those are just different flavors. Ultimately, if things converge, then you're good. And if things don't converge, then you're not good. The rest is really just a flavoring. Any other questions? All right. Well, and you can feel free to try this third one. Basically, we can actually see whether it converges. You can try it on your own. Okay, so now we will actually go to one more method that also starts from iteration and then improves as we go. And this is arguably one of the most popular methods, partly because when it converges, it's real fast. However, it doesn't always. And that theme kind of repeats itself in all of the root finding methods, that I don't have a guarantee of convergence. So unless I use bisection method. So this is motivated by Newton. Newton had his hand in a lot of things. This one is not an exception, also called as Newton-Raphson because Raphson later improved it. But basically, it does the following. It again improves. So let's say that I'm currently at iteration xi. Okay? And this is the actual function f that I'm looking for this root right here, the blue one. So what Newton says, okay, approximate this function with its slope. So that's essentially linearizing locally this nonlinear function got approximated as a linear, as a straight line. That's what basically slope does. So approximate this function, look at this slope, and basically just look at where does this slope or this approximation to the function, where does it intersect 0? And let that be your next guess. And then you repeat. Again, you look at the slope at this point, you find the slope, and you get real close. You can see how here, basically, in 2 iterations, I got really close to this root. So when you actually do, again, analyze this triangle, there's a lot of basic geometry in these methods by plotting graphs. This is my f of xi, okay? The slope of this is f prime of xi. This is the difference between my xi and xi plus 1. And when you basically arrange that, you will see that xi plus 1 is equal to xi minus f of xi divided by f prime of xi. I could also actually get to this approximation by looking at the Taylor series. Remember how that's a very important formula in calculus, and chopping off all of the higher order terms. Okay? And assuming that the value that I'm trying to get to is actually 0. So basically this can be also derived from Taylor series, but this is essentially my method. So this is it. Basically I have at this point, if I give you any method that I explain to you the motivation of the method, but I give you a method that gives me a rule of how to get to my next iteration from the previous iteration. So xi refers to the current iteration, previous iteration, however you want to call it. And then I have a rule how to calculate the next one. So you can easily modify the code you have to actually do Newton's method, right? And I'm just gonna, before we actually do that or comment on all of the methods and then try them out a little, basically, I can I want to comment on a couple of pitfalls that you can come into. The main problem with this method, it's great when it works, but when it doesn't work, I typically have a problem with f prime. I'm dividing by f prime. So that f prime of x is close to 0, okay? And that actually means that I'm at the minimum or a maximum of a function. Then I'm gonna start creating large numbers, and like numerics will just go out of the window. So here's an example of near 0 slope around here, and it could be even near 0. Here I'm actually around this bottom here. So if I try, okay, so let's say that I'm starting at x0 right here, okay, and then my slope sends me to x1 right here. Then I take this value here, and slope sends me down. And I'm going to kind of like play in this fishbowl, okay, around this bottom and never get out of it. So when I'm near a minimum, similarly maximum of a function, and actually away from the root, I'm not going to go anywhere. I essentially cannot get over that big hill. Right? I'm going to play in this bowl here because my slopes will keep sending me and alternate, and he'll stepping me on one side, the other side, one side, the other side, one side, the other side, and I'll never get out of it. Right? Whereas I have to somehow climb over this mountain and get to here. Right? So that's this problem of not being close to the root. So you won't be able to get over this mountain. Sometimes you also have what's called inflection point. Okay? And that's where f double prime is 0. So essentially, so let's try, if I try it here at x0, okay, this sends me here. Okay? Then this is my next value, so I go down to the function. My f prime derivative sends me here. And then this one sends me further away out of this plot. And then further away, and this is how I get to infinity. In the other one, I'm playing around with okay values, but I'm never getting to the actual root. Here, I'm just diverging and going to the infinity. Okay? So unfortunately, n0, just like if you really hit the zero slope, you divide by 0, you get infinity, your iteration is done. Right? So that's a true disaster. So there's no general convergence criterion. You kind of depend very much so on nature of the function, which is our common theme for all of the root finding. And the best is to actually be relatively close to the roots. So another variant of this very same method. So this one assumes you have function f, and you actually have a derivative that you program, right? So you program both function and the derivative of it. Well, sometimes you don't have that. Sometimes you actually have data. And you need to actually figure out, or numerically you have to approximate what the derivative is. And that's essentially a secant method. So basically it's going to use the Newton's method formula, but instead of f prime, I'm going to throw in a finite difference approximation to f prime. Okay? And that is basically the difference in the values divided by the difference in x's. Okay? That's my approximation to the slope. And when I throw that into the formula, I get this. So that's just basically motivated by Newton method. You just replace what f prime is. And again, you have, based on the previous value, you have your next value. Actually, in this case, to get that f prime, I need two values. So I'm going to have two initial guesses to start with. Not terrible. All right. So in review, we went over bracketing methods and open methods. In this new class of open methods, we had fixed point iteration, Newton-Raphson, and secant method. Fixed point iteration is kind of cute. It rearranges my original f of x is equal to 0 to something that looks like x is g of x, and then my iteration is real simple. My next iteration is g of the previous one. In Newton-Raphson or secant, my next iteration depends on the slope or how I estimate it. So I take f of x and f prime of x, and that basically builds my next iteration. So we can now do any of this. Which one do we first? So we had different f's in this simulation. This one is actually not, I did not show this example, but this was my Pengue-Robinson. This was my falling parachute. This was this polynomial that we just worked with. Pick one of them, and let's do Newton-Raphson method. So let's get practice here. Programming, so maybe start from whichever code you had previously. And since this one might diverge, I would keep this structure where you also limit the number of iterations. And I'm going to just start from here. But I'm not going to comment on what I'm doing. I'm just going to keep programming, and you program on your own. Yes, questions?
So for the Newton-Raphson method, would that only work for single roots or a double root?
Yeah, so double root will have that problem of being a fishbowl. Yeah. You could get to it as long as you, nearby a double root you have f prime close to 0. So
it wouldn't be like 3 roots?
Huh? Yeah.
Okay.
So. I call that the fishbowl problem around the minimum. reuse of the code at its best. The shell of all of the structure, number of iterations, initialization, it's all the same. All I changed is this line to be Newton's method. So my previous guess minus f of x, the previous guess, divided by f prime, I'm calling it df. And I just pre-programmed both f, I chose that polynomial just to go simple. Simpler to type. For Payne Robinson calculating df, I'm gonna make a mistake on the fly in front of the entire class, so I just avoided doing that. But it's really 5 lines that have changed. So when you write code, you want to do that. You want to have a well-structured code that you can easily reuse. Did everybody get the solution? What's interesting here, I found a different root. So where your method sends you matters, and how do you construct these next guess? So here those slopes in Newton's method send us to a different root, the negative one. Even though the starting point was 0, which was the same. At least that's how it's working for me. So, possibly. So I took that polynomial function. Let's see, what would we get for minus 100? Actually, got another one. So with 2 different methods, over the 2 different methods, I got all of the 4 roots. And all of them are real. That one that did not converge, or it went to a complex value. For whatever reason. So this function seems to be behaving with whatever starting point I take for Newton.
For your derivative, should it be 4 times x?
Ah, maybe that's why I'm converging. It should. Who knows what did I converge to? Okay. Yes, it should. Let's see now. Well, I still got to a value. Let's actually do. So that's my x to the 4, or print, minus x minus 10, right? That's not a solution. So I got stopped at 10 because my maximum of iterations was 10. Let's try 100. So this is divergent actually, because I had the typo. Let's put this as a f of x as a test. There we go, always important to have tests. Oh, so it actually did get it, but it took 18 iterations, and it got to that initial root from 100, I believe, starting from 100.
Your derivative. Your derivative
Was
minus 1. It's minus 10.
no.
Or the df.
Derivative of this is minus 1.
Oh, yeah. Oh, no.
Yeah, okay. That one I got right. But good, yeah, good to check always. This one, is derivative of this is nothing. Okay, so let's try. So let's now try all of them. So let's try starting from 100. I got to my 1.85, starting from a minus 100. I got to the negative one. Good. Starting from a 0. I still got to the negative one. Okay, and my f, it's not 0, but it's decently small. Okay. Did everybody get this? So we're not going to do this, but if I was actually now modifying this code to be a secant method that actually has this formula, how would I do this?
You need to initialize.
So I need to initialize 2 values, and then I would just always work with 2 values here. And then this update would update, it would move ahead 2 values, not just 1. So maybe I can call them x0 and x1, right? And shift both of those values and update both of those values. So those are the key differences. I wouldn't need this, the f of x. I would always work only with f. This formula would change. I would initialize 2 values and update 2 values. Again, about 5 lines of code difference, not a big deal. And to wrap up, okay, just a comment, we had that false position method, which was a bracketed method, that looked like it took the bracket xl xu that was around the root, and it had the formula that my next value that I'm looking to subdivide my interval xr is xu minus f of xu times xl minus xu divided by f of xl minus xu. That looks like 1 over f prime of x somewhat. And this is my secant method. So when I look at them, they look awfully close. I just kind of have different names. So what was I was u, was I minus 1 was L, and R is I plus 1. So it's almost the same, but not quite. I have to start from a bracket for false position, I have to know that the root is in between. And then I'm looking at that midpoint and then looking at the left side and the right side and figuring out what is my next bracket. So first one actually has guaranteed convergence because you found the bracket. In this one, you just start with 2 guesses and you go, right? And there's no guaranteed convergence. But the formula in itself is the same. So they look deceptively similar, but they're not precisely the same. Okay? And then if you were comparing in a structured way, which is what you're going to get for the homework that is going to be assigned today, it is in my email inbox, I believe, ready for a check. So basically what you do to compare different methods of the same problem is you calculate relative error at every iteration, and you kind of record that. And then you plot a graph like this, and see how does your relative error change, typically logarithm of the relative error. Hopefully it's going down really quickly, and then you're just looking at the log values as opposed to the values themselves. So then you look at the logarithm of the value versus the number of iterations. Typically, again, we've seen already that's not always the case, and I very much depend on a function, but typically bisection will be the slowest, and then you will have false position secant. And Newton-Raphson is what's called quadratic convergence, so the slope of this is 2 on the log scale. And when it's linear convergence, the slope on the log scale is 1. And you will get to compare how does this how does this convergence work for some problems in your homework. But that would be sort of like as an engineer, if you get a problem that requires this, you would go on your problem and evaluate which of the methods works the best, especially if you're going to do this a million times after that in a simulator, right? So you do want the fastest one and kind of come up with a good scheme of where to start your iteration so that you have a successful iteration over however many times you're executing this code. And that essentially, well, now you can go on changing the methods. So basically, you could also have a modified secant method where your f prime is estimated as like this. So just using some value d, slightly away from its side. So I could now come up with 5 more methods with variants like this. So to an extent, I will, for exam, you will have all of these methods written down, like what their formulas are. So if I ask you, hey, implement this and this one for a specific problem, you can immediately do that. But also I could just ask you, hey, here is this new method called blah, and here's the formula for the next iteration based on the old one. You need to be able to just write a code that does that. So on a certain level, it doesn't really matter as long as you know what the next iteration is, and you know how to analyze it. If you were working with it, you can figure out how the relative error goes down, and you can evaluate whether it works for you or not. Okay? And then somebody already mentioned multiple roots. Multiple roots are a problem. So it refers to equations such as like this, f of x, where I have x minus 1 is technically double root. Okay? And then I have this quadratic function behavior near the root. I'm sitting on x is equal to 0, but I'm either negative on both sides or positive on both sides, and then my bracketing methods don't work. So for polynomials, we have methods that work with that. Otherwise, it's problematic specifically for Newton's method. Okay? All right. And we are programming ourselves, but Python does have ready-to-go functions if you want to just test them out. Okay? All right. We're done with root finding, starting linear systems next time.